Hi, this is Mike Garrison from Fair-Rite products. In this video we're going to be doing a little bit of a comparison between two common open magnetic structure type cores. The rod type core and the bobbin type core. And before we go into some of the similarities and differences between these two different core types, let's take a look at what we mean by open magnetic structure core. So really quickly, this is what we consider a closed magnetic structure core. This is a toroidal type core. When we say closed magnetic structure, we mean that all the flux is contained within the confines of the core. Now, an open magnetic structure core, the flux is able to travel outside of the confines of the core. And we'll take a little look on my computer screen at what we're meaning, a little bit of a visualization of what we're talking about between those two different core types. Here we are in the FEMM plugin for Octave. This is a representation of a toroidal type core, which, as we discussed, was a closed magnetic structure type core. This ring here is the ferrite material. Here we have the windings of the core. Inside of here is air. Outside of the confines of the core is also air. Let's take a look at how the flux travels in this simulation through our closed magnetic structure type core. And we'll compare that with a rod type core as an open magnetic structure, and then we'll look at how the rod type core differs to the bobbin type core. So we can see here these lines here represent the flux traveling throughout the core material, and for the most part the flux stays confined into the core material and not in the surrounding medium, in this case air, aside from a little bit of fringing that we get from the windings. Now let's take a look at how that differs from a rod type core. So we have here our rod type core. This rectangle in the center represents our core material, and these upper and lower rectangles represent our winding. Again, this is all placed within air as a medium, and when we look at our simulation, we can see the flux is, for the most part, not contained within the core material, but rather propagating out from the ends and traveling around back through the core. Now, this is why this is considered an open magnetic structure. A significant portion of the flux is traveling through open air, or whatever our medium happens to be. Now let's see how a bobbin type core differs to a rod type core. This is our bobbin type core. Again, the center section and these flanges on the end represent our core material, and we have our winding on the top and bottom, and everything is housed within air. Now this is roughly the same dimensions as our rod type core in terms of the diameter of the center post and the overall length of the core and the positioning of the windings within that core. When we look at our simulation, we see a similar effect to the rod type core in that the flux is propagating outwards from the core material, although it is to a much lesser extent than what we saw in the rod type core. This means that in general, a bobbin type core is going to see less of the flux travel through open air, or again, whatever medium it happens to be in, relative to a rod type core. So now that we've taken a look at a little bit of a visualization on the magnetic pathing, or the flux pathing, in a bobbin type core, a rod type core, as well as how those differ from a closed magnetic structure type core, such as a toroid, let's talk a little bit about some of the practical considerations on using each of these types of cores and how they differ from one another. So the primary difference between these is going to be how much of the magnetic path is through free space or air as a medium, as opposed to through the core as a medium. The more of the magnetic path that is going through air, the more dampened the properties of the ferrite core are going to be. So right off the bat, a bobbin, generally being a similar size and diameter as a rod, is going to see less of that magnetic path length be through air, since a lot of the flux is being channeled through those flanges and across one another. What we saw on the rod was the fluxes kind of propagating out from the ends of the rod and around, meaning that as a percentage, the less of the flux is contained within the confines of the core. So what does that mean? The most obvious one right off the bat is that rods generally are going to have a lower AL. And what we mean by AL is inductance factor. So that is amount of inductance per turn when the cores are wound. The bobbins, therefore, are going to have a relatively speaking higher AL value. Now, that may off the bat seem like bobbins are better, but it's really application dependent. Sometimes a super high AL isn't always desired, but rather some of the other properties that are dampened by that larger path length going through air are desirable. So rods are going to have a lower effective temperature That's to say that the outside ambient temperature or internal temperature of the core is going to have less of an effect on that inductance value than it would on a bobbin, where more of the flux path is through that core material that can be more affected. And the same thing can be said with a high DC bias current. So having a very large DC bias current is going to affect a rod type core less than it will a bobbin type core. So we have our AL, temp coefficient, and DC bias. Now let's talk a little bit about the mitigation strategies for both of these cores, because it kind of differs. So when you're trying to mitigate DC bias and temp coefficient on a bobbin type core, the solution is generally to make the core longer, therefore increasing that as a percentage, increasing that distance that the magnetic path length is traveling through free space. Now that differs to the mitigation strategy on a rod type core. A rod type core, you want to shrink the length of that down, since that will cause more of the flux to travel through air as a percentage than through the core in the center. So a little difference in how you'd actually mitigate both of those factors when dealing with the two different geometries. Let's talk about some just general practical considerations of these two types of cores too. Definitely the performance, and again it's application dependent. Sometimes an application will value higher AL, sometimes lower change due to DC bias or temperature is what's desired. But let's talk about some of the practical considerations of them too. Now right off the bat, a bobbin type core, it's easier to wind. You can wind directly on here. The flanges are going to contain the winding within the confines of the core. You won't have anything spilling out. It could be a little bit more neat. But rod type cores, while they're more difficult to wind directly, the not having flanges on the ends allows you to use coil formers or pre-wound coils on there and simply slide them through and adhere them somehow. So bobbins may be easier to hand wind, whereas rods might be a little bit more producible on a large scale when using coil formers. And another consideration is price of the two. So rods and bobbins both start out as a similar cylindrical type core. Rods, some of them and some of them won't, will be centerless ground on the outer diameter to get them to a more precise size, as size is a crucial aspect of the performance of the core. And bobbins will often see that same process. But with a bobbin type core, either material has to be ground between the flanges in order to create the flanges from a cylindrical type core, or the flanges may be adhered on after the fact as two separate cores. Now, this extra processing does tend to mean that bobbins are going to be, in general, a little more expensive than a rod type core, just being a more complex geometry, either through assembly or additional machining processes or whatever the case may be. So that is also something to consider between these two types of cores is, the mechanical, let's write that down here. So price lower, price higher. And we're going to put winding in the center with a question mark, because it really depends on how the cores are going to be wound. So hopefully this gives you a little bit of insight between these two types of core geometries, why you might use one versus the other depending on what's needed in your application. And with that, this is Mike Arison from Fair-Rite Products, and thank you for watching.